Click the bell icon to get latest videos from Ekeeda.
Hello friends, in this video we are going to see non-inverting configuration adder. How non-inverting configuration can be used as an adder. In previous video we have seen summing amplifier using inverting configuration. In today's video we are going to see summing amplifier using non-inverting adder. Let's see the circuit diagram for a non-inverting adder. Here also non-inverting adder can be called as a summing amplifier since it adds different voltages. Here you can see non-inverting terminal. Here the input voltages are applied to the non-inverting terminal. Inverting terminal is a grounded. RF and R1, these are here the resistance RF and R1 will provide the closed loop gain. Since it is a non-inverting configuration, closed loop gain of an amplifier will be 1 plus R1 upon RF. VA and VB are the input voltages which are given to the non-inverting terminal. RA and RB are the resistances which are connected to the non-inverting terminal. IB1 and IB2 are the internal currents which are usually 0 if this is the ideal op-amp. Now let's see how the expression for output voltage can be derived. Basically we should know that if it is a summing amplifier, then my output voltage expression should be VA plus VB, that is two input voltages addition should be there as an output voltage, and there should be no negative sign because it is a non-inverting adder. So output should be equal to V0 is equal to VA plus VB. Expression for output voltage. Now here we have to apply superposition theorem. That means at a time only one source will act. Since we are having two input voltages VA and VB, at a time only one will act. That is, if VA is working, VB will be 0. If VB is working, VA will be 0. Now in first case, case 1, let's consider VA acting alone. That means VB is equal to 0. Since VB is equal to 0, this terminal is grounded. VA is acting alone and the configuration will look like this. Now by superposition theorem, if I want to find out the voltage across V1, because the input to this operational amplifier is voltage at this terminal, because this is the input voltage, but due to the resistances present over here, at this terminal voltage will be different. Let's say the voltage is equal to V1 dash. So V1 dash can be written by using potential divider. By using potential divider, we can write V1 dash is equal to total voltage, that is VA, into the resistance RB divided by addition of these two resistance RA plus RB. This is what we called as a potential divider or voltage divider rule. Let's say this is equation 1. Now this equation we have got for VA acting alone. Now next case will be VB will be acting alone. Let's see what is case 2. In case 2, consider VB acting alone. That means VA is equal to 0. So here in diagram you can see this is grounded because VA is equal to 0 and VB is acting alone. So here also the input voltage is nothing but the voltage across this terminal. Let's name it as a V1 double dash. So V1 double dash can be written as VB, that is the total voltage, into this resistance RA divided by RA plus RB. Let's say this is equation 2. Now V1, that is V1 is nothing but it's an addition of equation 1 plus equation 2. So equation 1 is nothing but VA RB upon RA plus RB and VB RA upon RA plus RB. Now here we want output voltage is equal to addition of VA and VB, those are input voltages. That means anyhow we have to remove this term. Now how to remove this term? Now we know that here the output voltage is equal to closed loop voltage gain and input voltage. And since we need V0 should be equal to VA plus VB, that means there should be no other term. Now if you see the AVF, it will be 1 plus RF upon R1. That means we have to make the adjustment with the different resistance in such a way that in output expression only VA and VB should remain. Now let's assume that RA is equal to RB is equal to R. If you substitute this in equation, RA divided by RA plus RB and RB divided by RA plus RB, this will become 1 R upon twice of R plus R upon twice of R. Here we have VA and here we have VB. Then this RR will get cancelled out. From here also RR will get cancelled out. So only thing will remain VA divided by 2 and VB divided by 2. So the equation will become V1 is equal to VA divided by 2 plus VB divided by 2. Now closed loop gain of an op-amp is AVF is equal to 1 plus RF upon R1. Here let's take RF is equal to R1 is equal to R. Then this will become R divided by R, that is nothing but 1. So 1 plus 1 will become 2. So here AVF is equal to 2. Now let's substitute AVF is equal to 2 and V1 is equal to VA by 2 plus VB by 2 into this equation. So if you substitute AVF value is this and V1 value is this, then V0 2 will get cancelled out and your V0 will be VA plus VB. So here you can see the output voltage is nothing but the addition of VA plus VB. Since it is called as an adder, there is no phase shift, so it is called as a non-inverting adder. So non-inverting configuration can be used as an adder. I hope you have understood how adder can be implemented by using non-inverting configuration of op-amp. Thank you for watching this video. Stay tuned to Ekeeda. Do subscribe Ekeeda. Thank you so much.